Okay, my pleasure to be here. I'm going to talk about reinforcement learning and model predictive control, their connections, and also the underlying methodologies and some applications. And the lecture is based on my ASU course that I've given for 7 years now. And I've written several books during this period. And the ones that the most closely connect to the content of this course is this one, Lessons from AlphaZero. It's a short book, about 250 pages, kind of intuitive, visually oriented. I think it's a very good entry point to what I'm going to discuss. This is my textbook, the one that I use in my class. It's in the second edition now. And the print version is going to come out in the summer, but there's a complete internet version that has been recently updated, particularly during this latest offering of the course. There's also a survey paper on reinforcement learning and model predictive control from last year, and I think it's, and there's a video lecture associated with that. They can all be found on the internet, and they're all very relevant to this lecture. And this is a mathematical book, Abstract Dynamic Programming, which has a lot of the mathematics and the intuition behind the more visual interpretations that are contained in these two books here. Okay, I'm going to attempt to give you a one-slide overview of the field and also my lecture. I view reinforcement learning as the art and science of solving optimal sequential decision problems approximately. And now dynamic programming also addresses optimal sequential decision making. So reinforcement learning deals with exactly the same mathematical problem as dynamic programming. And let me get back to this word here, approximately. In dynamic programming, there are two major objects that we want to approximate. One is value functions or cost functions, and the other is policies. So the field naturally bifurcates along two strands, approximation in value space and approximation in policy space. And these two strands are somewhat related, but they're also different in fundamental ways. Approximation in value space is very much connected with the core theory of dynamic programming. It's connected with MPC, model predictive control, a lot, and also at a more fundamental level with Newton's method for solving Bellman's equation. Approximation in policy space, on the other hand, is somewhat connected with dynamic programming, but it's more connected with nonlinear programming, like gradient-like optimization, policy gradient methods, the PPOs that you hear about, and also random search. Now, the emphasis in my books, in my course, and also in this lecture is going to be on this blue strand. And I'm not going to go into this one, but keep in mind that there's significant separation between these two. So I'm going to go down this path, focus on Newton's method, and focus on extensions of the methodology near the end. So I'm going to start with a basic connection between reinforcement learning and MPC, and I'm going to use computer chess as a vehicle for that. Then I'm going to talk about the Newton theoretical framework, which is recent. It was developed while I was teaching at ASU, and I think it helps me a lot understand the various methodologies, categorize them, view the synergies, and also provide some guidance on how to select methods to apply to a given problem. And all of this is going to be one-step look ahead. And then I'm going to go into multi-step look ahead. Then I'm going to discuss the issue of superlinear convergence that accompanies Newton's method and how it affects what I call the critical mapping between approximation error and performance error. And then at the end, I'm going to give you an overview of some of the things that we're doing at ASU, and with a special focus on Minimax problems and also in some work that we have done on computer chess using MPC. So let me get started with computer chess and the AlphaZero program, an amazing program that created a lot of enthusiasm about the prospects of reinforcement learning. And it plays chess and also other games, but I'm going to focus on chess. Like most chess programs, it involves two algorithms. A lot of people don't realize that there are two separate algorithms involved in AlphaZero. One is the offline training algorithm, whereby the program learns how to evaluate positions, and it does so by using deep neural networks, self-play or policy iteration algorithms, and this algorithm operates before the program plays any games against a human or computer opponent, just offline training. And then there's the online play algorithm, which is the one that's used to select moves against a human or computer opponent online. And this involves a different process: multi-step lookahead, minimization, optimization, position evaluation at the end, using the position evaluator that was obtained by offline training. Now, most of the attention has been focused on the offline training algorithm because it involved innovative neural network technology and also other things, Monte Carlo tree search, and people have focused on that a lot. The online play algorithm is not so new. It's more or less traditional, but however, it's the one that's critically important for good performance. It's not this stuff that carried the day. It's this stuff in combination with offline training. And now the online play algorithm in computer chess is very strongly connected with MPC. Basically, I'll argue that they are isomorphic at some conceptual level. And there's an important question: how do the two algorithms, offline training and online play, how do they connect? And my answer to that is going to be Newton's method. So I'll get into this, but let's set the stage first for model predictive control. It involves multi-step lookahead optimization with a cost function approximation at the end, and the approximating function is I'm going to use J tilde. I'm going to use tilde to denote approximate stuff. So I'm going to use as a vehicle discrete time deterministic optimal control, whereby there's a dynamic system equation. Xk denotes the state at time k, Uk denotes the control at time k, and the next state is generated from the current state and the control that you apply using this equation involving this known f function. And at every stage, there's also a cost that depends on state and control. And the objective is to minimize the sum over all costs over an infinite horizon. And the way MPC works, when you are at the current state, this is the online algorithm. When you are at the current state xk, we apply a control obtained by solving an optimization problem, an L-step look-ahead optimization problem with a terminal cost function J tilde, a given somehow obtained terminal cost function, perhaps by offline training. And mathematically, the problem is to minimize, starting at time k, find an L-step control sequence that minimizes the L-step cost, the next L steps, and the cost of the future as approximated by this J tilde function. Xk plus L is the state that you get at after L steps, and this quantity here quantifies the future cost. So present cost for the next L steps and future cost, we minimize that, we obtain a sequence of L controls, we apply the first control in that sequence, and we discard the remaining controls, and then we go to the next step at state xk plus 1, we do the same thing and continue for a number of steps, and in this way you get a policy. You get an assignment of a control to a state for every stage. So that's what MPC is, and of course there are extensions to stochastic problems, to min-max problems. There's a lot of different versions of it. I'm giving you the simplest version. Now let's look at online play in computer chess after we have done offline training and obtained a position evaluator. at the current position, which is the current board position, that's the current state. We look at all possible controls, all possible legal moves. Then we consider all possible legal moves of the opponent, then some more moves of our moves, and then the moves of the opponent, multiple stages up to a certain level of look ahead. And then the position that we obtain is evaluated by using the offline obtained position evaluator. And then the scores are backed up to the root and using some form of dynamic programming. And the move that has the best score is used at that position. Then we go to the next position and so on. So if you look at it, it's again, multi-step look ahead with position evaluation at the end. So it's the same thing as MPC. It's isomorphic to the MPC architecture, but there are some differences. The first difference is that in chess, the state and control spaces are discrete, okay? Finite number of moves, finite number of positions. Whereas in MPC, they are usually continuous. The original research on MPC was for continuous space problems. And nowadays, MPC is applied more broadly, but the starting point and part of the significant range of applications is continuous. Here's another difference. In chess, the look-ahead tree is usually pruned. We don't search throughout the entire tree, but parts that are thought to be not promising, insignificant, they're pruned off to expedite the computation. In MPC, the look-ahead optimization is usually exact, but then I'll mention a few things later about that. So that's a difference. However, these two differences are inconsequential at the fundamental conceptual level, because what I'm going to describe as our Newton step theory works for arbitrary state and control spaces and inexact look-ahead and covers everything that's common to MPC and computer chess and beyond. And finally, there's another difference. Chess is a two-player game. It's the player and the opponent of the player. And whereas in MPC, usually there's only one minimizer. And however, think of chess against a fixed opponent. Then it becomes a one-player game if you fix the opponent. And I'm going to come back to this idea later. So we have a connection between MPC and computer chess. The points I'm going to touch upon in this talk are, first of all, that online play with one-step look ahead can be viewed as a single step of Newton's method for solving the problem's Bellman's equation. And the significance of this is quite profound, I think. And there's a similar interpretation that applies to multi-step look ahead. Now, the online play is a step of Newton's method, but offline training provides the starting point for the Newton step. So that's also important. It's important to have a good starting point for the Newton step to accelerate convergence. But the online play is the real workhorse. That's where all the magic happens. The offline training is, okay, has attracted a lot of attention, but that's not what it is, okay? It's mostly the online play that's the important part, and offline training plays a secondary role, in my opinion. Something that I mentioned earlier, the Newton step framework is very general because it's couched on abstract dynamic programming ideas, arbitrary state and control spaces, stochastic problems, deterministic problems, hybrid systems, multi-agent systems, finite infinite horizon, discrete and continuous optimization. All of this is covered, even though I'm going to focus on a very simple example to illustrate the Newton step. The ideas are very general because everything is couched on abstract ideas of dynamic programming. And then in the end, I'm going to discuss how Newton step framework does not quite apply as well as for single player problems, does not quite apply as well for minimax problems. And we will talk about a modification based on the idea of a nominal opponent, and we will illustrate it with computer chess. A nominal opponent is a player, a fixed player, to replace the maximizing player. So from minimax, we can pass to min. So now let me get into the Newton theoretical framework. Like I said, this is all very general, but for the purpose of visualization and for explanation using a familiar context, I'm going to talk about the linear quadratic problems. One-dimensional linear quadratic problems where xk and uk are scalars, and the system is like so. So this is a linear system. A and B are fixed scalars, known scalars. Xk is the state, uk is the control. So it's a linear system. And the cost is quadratic. There's a quadratic term in the state with q being a positive scalar, and a quadratic term on the control with r being a positive scalar. And this is a very well-known problem, a very fundamental problem in control theory. And the basic fact is the optimal cost function can be addressed by dynamic programming. The optimal cost function is a quadratic function of the state. And the optimal control policy is a linear function of the state. And the formulas are what you will see here. And it's not important to remember the formulas, but the basic fact is that the optimal cost function, which I denote by J star will always be the optimal cost function for this problem, is quadratic in the state, with K star being some scalar, a positive scalar, which is the unique positive solution of the Riccati equation. That's how this K star is computed, by solving this Riccati equation, which is a fixed point equation. K equals to f of k, where f is a function or an operator, which I call the Riccati operator. It's given by this expression. This is a nonlinear function, concave function. I'll illustrate in the next slide. We solve this equation, obtain K star, and that gives us the optimal cost function. Given K star also, we can obtain the optimal policy, which is linear of this form, with L star being a scalar given in terms of K star and the data of the problem by this formula here. So solve the Bellman equation, find the fixed point of the Riccati operator, and then compute the optimal policy, which happens to be linear like so. And all of this, of course, generalizes to a much broader setting, but I'm going to focus for the moment at linear quadratic problems. So now let's look at a visualization of the solution process. We want to find a fixed point of the Riccati equation. Remember, the right-hand side of the equation, of this equation involves the Riccati operator. It's given by this, and its graph is what you see here in red. This red curve as a function of k. So this is k, and f of k is the red curve, and this is a faithful illustration. Indeed, it is concave, smooth, and approaches some asymptotes on either side. And the solution, the optimal cost function coefficient K star, is obtained as the fixed point of this Riccati operator. And the fixed point is obtained by finding the intersection of the red curve with a 45-degree line, which is the graph of the function K. So K equals f of K. And this is K star. And to find K star, you can obtain analytically, but you cannot obtain analytically. But in general, you can obtain computationally by means of the one possibility is the value iteration algorithm, VI, the value iteration algorithm. And it generates iteratively the optimal cost functions of K-stage problems. Our problem involves infinite stages, so the value iteration generates the optimal cost function of a one-stage problem, then a two-stage problem, and so on. And it has the property that it converges to the optimal cost function. And the way it operates is as follows. The cost function of the k-stage problem has this form, with kk being a scalar, and it's obtained by iterating with the Riccati operator. So for the coefficient of the k stages problem, you obtain the coefficient of the k plus 1 stages problem by iterating with the Riccati operator. And graphically, what you do at the typical iteration, here's kk, you obtain kk plus 1 by going up here. Then you reflect this along the 45-degree line. Here's kk plus 1, then this is kk plus 2, and so on. So there is this staircase process by which value iteration approaches k star. Okay? And k0 is some positive or zero initial condition. So now we've given the Riccati equation for the Riccati operator for the minimization problem. However, there is a Riccati equation for linear policies also, and consider a linear policy of this form, linear in the state. So given L, the policy is of this form, and it has a cost function. We plug it into the cost, and we obtain a cost function. And this cost function happens to be also quadratic, quadratic in the state, involving a coefficient KL, depending on L. And it's the unique solution of another Riccati equation for policies, linear policies, also called a Lyapunov equation. So again, the cost function of linear policies is obtained as a fixed point of an operator that has this form, and now this form is linear in K. The Riccati equation for policies, the Riccati operator for policies is linear, and this is the coefficient of K, and this is the constant, okay? And so the graph of this policy, the Riccati operators, are lines like this, okay? And for different values of L, you get a line, another value of L, you get other lines. Now, some of these lines have a slope less than 45 degrees and correspond to stable policies, where the coefficient of K is less than 1, and some others have slope greater than 90 degrees, correspond to unstable policies, for which the cost is infinite. Now, for the stable policies, the corresponding cost, the cost coefficient, KL, is obtained by solving a fixed point problem again. It's the intersection of the policy line and the 45-degree line. And you obtain this KL, which is obviously to the right of K star. K star is the optimum. So for unstable policies, of course, the corresponding cost is infinity, and we're not interested. There is a fixed point, but the fixed point is over on the negative axis and doesn't matter. It's not meaningful. So we have the min Riccati operator and the mu Riccati operator, and let's see how they connect. Well, the important thing is that here's the min Riccati operator and the policy lines here, and the red curve is obtained as the lower envelope of the lines. There are many, many lines here, and if you bring them as low as possible, they envelop this graph here. And this is expressed by this equation. F of K is the minimum of all the FLs of Ks. So, that's the relation. And suppose now that you make a cost function approximation, like K tilde. This corresponds to J tilde that I mentioned earlier. How would you obtain the MPC policy? Well, what you have to do is look at all the policies and the intersection of and their values, the values of their lines at the point K tilde, and find the minimum one. So the MPC policy for a given K tilde is obtained by going down on this line up to the point where there's a line that just touches this red graph. And it has to touch because otherwise, because this red curve is concave, so it cannot cut across, okay? It has to touch exactly at this point. So the MPC policy, what it does, it linearizes the Riccati operator at this point K tilde. And that's the MPC policy, or the line that corresponds to the MPC policy. And the corresponding cost function is obtained as a fixed point of this line. It's this KL tilde. So you plug in K tilde as cost function approximation, and you obtain a policy that's obtained by this linearization process. But this linearization process is exactly Newton's method. That's what Newton's method is, as you learn it in calculus. Now, what you learn in calculus is not the most general. It applies to differentiable costs. In dynamic programming, very often the Bellman operator, which is related, of course, to the Riccati, Bellman operator is not differentiable. Could be piecewise linear, could be non-differentiable. For problems, the classical problems of dynamic programming, it is concave, and that's the important thing. And the theory of Newton's method applies to concave and convex fixed point problems. By, instead of linearizing using gradients, you linearize using subgradients. Now, this is a theory that's not very well known, but it exists since the late 70s. And there's a very comprehensive theory. And there is convergence analysis, superlinear convergence analysis. Everything goes through in a very nice way. And all of this, okay, there's a lot of literature, but you can find an overview of this as well as a relatively simple proof of convergence and rate of convergence in this Lessons of AlphaZero book. In appendix, there's a very good starting point to the theoretical aspects of Newton's method for non-differentiable Riccati operators. So all of this generalizes very broadly. And now, okay, so let me reiterate this Newton step visualization. You have K tilde, the cost function approximation. MPC does this linearization. The fixed point corresponds to the one-step look-ahead policy, the MPC policy. And because of the superlinear convergence property of Newton's method, the error between one-step look-ahead policy and the optimal policy, this thing here, is much smaller than this error, which is the approximation error, provided, of course, you are within the region of convergence of Newton's method. If you're outside the region of convergence of Newton's method, this does not apply at all. And in my opinion, this explains the excellent performance of MPC in practice over many years. MPC has been around for 40 years or so. It's really the workhorse. People trust MPC. It works in many contexts, not only in ordinary control, but also in adaptive control. It's really a method that has proven its value again and again. And the reason is that this Newton step at its core. Now, this is for one-step look ahead. So let's see what happens with multi-step look ahead. Now, the thing to remember about multi-step look ahead is that it's really one-step look ahead, but for a different starting point. L-step look ahead on K tilde is the same as one-step look ahead on K tilde after it has been operated upon L minus 1 times with a value iteration operator. So basically, look at this picture, two-step look ahead, one step, second step, and then we take the quadratic cost function approximation. The Newton step is the first step, only the first step, but it operates on all the rest, both the remaining part of the look ahead as well as the cost function approximation. So that's the once you understand that, there's no difference between one-step look ahead and multi-step look ahead. So here's an illustration in terms of our earlier figure. Let's look at MPC with two-step look ahead. You start at K tilde, you do one step of value iteration, and then you take the Newton step. If it was a 10-step MPC, you would operate on K tilde 9 times with value iteration, bringing the result closer to K star, and then take the Newton step. And Important point here is that the multi-step lookahead brings the starting point of the Newton step closer to K star. So the more lookahead you have, the more you bring your starting point closer to K star, accelerating convergence and also escaping, getting yourself into the region of convergence of Newton's method. Because K tilde may start outside the region of convergence, may correspond to an unstable MPC policy, but with multi-step lookahead, you stabilize that policy by bringing the starting point of the Newton step within the good region. Okay, so let me elaborate on this point. The importance of the first step of lookahead. Only the first step is the one that does the magic, and the remainder plays a subsidiary role to help the Newton step. So only the first step of lookahead acts as the Newton step, and the remaining L-1 step serve to enhance the starting point. And there's an important insight here, practical insight. The first minimization step in the lookahead minimization should be done exactly. Otherwise, you don't get the Newton step. However, the remaining steps can be done approximately. They just move around the starting point. But if you are within the good region, roughly, then it doesn't matter exactly where you are. So for example, in stochastic problems, where doing multi-step lookahead is very expensive because of the rapid growth of the lookahead tree, we can use approximations such as certainty equivalence approximations for all the lookahead steps except the first one. The first one should be stochastic. The remainder can be deterministic approximations or other kind of approximations. And this was implemented actually and determined a long time ago in a paper that I had from 1999 for traveling for stochastic scheduling problems, where we applied the certainty equivalence approximation just on an intuitive basis, but we verified that it worked very well. Now, since that time, there had been a lot of verification of this point. And it's really, from an implementation point of view, it's an important point. Okay, so let me go a little further into the issue of superlinear convergence and the critical mapping and what its practical significance is. So here is again one-step look-ahead MPC, and the one-step look-ahead MPC policy, this mu tilde, at state X, it applies a control that's obtained by this minimization, involving the first step and the future as approximated by J tilde. And the important mapping here, what I call the critical mapping, is how cost approximation and the approximation error affects the performance error, the cost function of J mu tilde, and how far it is from the optimum. This is the critical mapping. Everything, that's the most important thing to look at, how your approximation affects the performance error and how to improve this approximation, of course, to improve the performance error. So there are some interesting questions here, like what is the relation between J tilde and J mu tilde? What's the role of multi-step look-ahead here, where you have a more complicated problem? And how does the size of the look-ahead affect this relation? And here's a figure that's a little schematic. It's a conceptual figure. For different types of problems, it may take a different form. But here I have plotted the approximation error, J tilde minus J star, against the performance error, the MPC policy minus the optimal, the cost of the MPC policy minus the optimal policy. And this relation is superlinear because of the Newton step. So it looks like this. For approximation error within the region of convergence of Newton's method, you get an almost optimal MPC policy. But if you are outside the convergence region of Newton's method, then you get catastrophically large performance, poor performance, and the method does not work at all. Now, the classical error bounds in this region sort of assume that there's a linear relation between these two. And that's wrong, completely wrong. If you try those bounds in real systems, then you see that the reality is not linear at all. It is, in fact, superlinear, and there's this separation between a stability region where things work very well and an instability region where things do not work so well. And the difference between one-step look ahead and multi-step look ahead is that for multi-step look ahead, this curve is more benign, it's more favorable, okay? The stability region is enlarged, the instability region is shrinked. And the more look ahead you have, the better off you are. Of course, it costs more computation. Now, there's another insight that I'll try to explain to you, namely the fact that, okay, how does this affect design? How do you choose J tilde? J tilde, the cost function approximation, is very often obtained by using a neural network or some kind of a rollout, the approximation of a cost of a policy. But it depends basically on two things: the limitation of the cost function approximation method, the approximation architecture, how powerful your neural network is, how good your rollout policy, your base policy rollout is. And it also depends on the training error because, okay, you have a good architecture, but you have to train it. And then there's an approximation error, which is inherent to the architecture. And there's a training error due to the fact that you haven't collected sufficient data, you haven't explored enough the space, and things like that. And from this figure, you see that the important thing is the architectural error. Whether your starting point is right over here, training will perturb a little bit, perhaps will bring J tilde to a little bit more favorable position. But once we are deep into this area, no matter how much data you collect, no matter how good an approximation method you use, the training method is, it doesn't matter. You're going to fail catastrophically because the approximation architecture is not powerful enough. And by contrast, if you are within the stability region, then it doesn't matter how much you train. You may train a lot or you may train very little, but it won't make any difference because Newton's method, once you are within the region of convergence, just zooms in to the optimal, and small variations in starting point don't matter at all. So there's a lot of practice in this field that is not in accordance with this viewpoint. People think that by training and training and training, you're going to get eventually something good, but it's not true. There are other things in play, including the fact that you need large multi-step look ahead, long look ahead to have success. Like AlphaZero succeeds not because of the neural network at all. It succeeds because it has very long look ahead, has 20 moves forward, 30 moves forward. And the approximation that you obtain from a neural network, which is trained in months and months of very sophisticated forms of training, this doesn't matter all that much. It's the long look ahead that's the workhorse in this process. So that's what I'm pointing out here, that inside the two regions, better training, more data, improving confidence intervals. There's a lot of work on confidence intervals in this field. Is it interesting? To me, no, it's not very interesting because of this figure here. All of these have marginal effects. The important thing is long look ahead, good approximation architecture. So, okay, are there any questions here? Because I'm going to go now into a review mode of what we have done at ASU.
So I have a question, and we've talked about it before, but I wonder if there's any insights. Is there any way of knowing a priori whether you're in this stability region?
Theoretically, no. And in general. Experimentally, you will know, okay? The system will break down. And then what do? Well, the thing to do is not try to collect more data. The thing to do is increase the look ahead or look for a different approximation architecture. Okay, it's so empirically, with the theoretical background as guidance, you can try various things, experiment, and that usually works. Actually, I found that in my experience, if you know what to look for, then the result of the experiments give you a lot of guidance on what to do next. Yeah.
One question. So, experimentally or in theory, how would you determine how long of a look ahead to need?
You don't know.
So you try.
It depends where you start. If you start right over here, your approximation architecture is right over here, then you need a longer look ahead to bring this green curve further down to bring you into the stability region, to expand the stability region. There's no way to know how long the look ahead should be. There's an interesting theoretical result, by the way, that for the classical problem that people try is this finite state, finite control, discounted MDP, okay? What you see in most reinforcement learning papers, the 5 tuplets, space control, discount, all of this. For that standard problem, you can prove theoretically that regardless of J tilde, how far away you are initially from your approximation architecture from J star, if you choose the look ahead long enough, then you're going to obtain the exactly optimal policy. Exactly optimal. The MPC policy, the L step MPC policy is going to be optimal for L large enough. That's a theoretical result that's been known since the 60s, maybe 70s. I mean, it's been well known. Not well known, but known. So
it's some degree seems like to be the exact dynamic program where we look into all the things possibility for a very long time.
yeah, you can visualize this result very easily because the Bellman operator is piecewise linear. So at the optimum, there's a linear segment. And if you apply long enough look ahead to bring the starting point for the Newton step within the range of this linear segment, you're going to converge in one step, okay? This is a very transparent result to understand for this particular type of problem. Of course, for smooth Bellman operator, this is not true, right? It has to be a piecewise linear kind of Bellman operator. Yes?
Do you get this? So for example, if instead of exact look ahead, you're doing approximate look ahead, something like pruning, do you get a sense of whether the important thing in general is depth of search? Like, is it still L steps if you're doing pruning, or is it really important that you have coverage of the space at a lower look ahead?
No, the intuition that you get from these figures, and a lot of figures of this type, including for pruning and also for limited, including for pruning. The important thing is the first step of look ahead has to be exact. And then, generally speaking, of course, the less you prune, the better it is, but it's not critical. But what's important is to go to increase the length of look ahead. That's the thing. Yeah.
I was wondering, does this assume any kind of
Can you raise your voice a little? I can't hear you. I'm sorry.
does this assume any kind of statistical properties of your approximation error? Like, does that have to be unbiased, or are there things that can kind of mess this up?
If you are with the good region, doesn't matter. If you're far away, again, it doesn't matter. Okay, it's biased, unbiased, a good confidence intervals, a statistical collection method, the method of processing the data, the way you explore the space, it's marginal. Okay, so, okay, some of the work that we've done at ASU, most of our work involves discrete state and control spaces, like combinatorial problems, or generally this games, discrete problems of all kinds, like traveling salesman, vehicle routing, scheduling, things like that. Okay, when Stephanie was at ASU, and also after she came to Harvard, We did quite a bit of work. Sushmita was one of the primary authors in this, Daniel also, maintenance repair, multi-agent robotics, taxi fleet management. And this work is very much continuing and alive. Recently, we've done work on data association, multi-target tracking. It's an important problem. And we have an application of this methodology, of MPC type of methodology, approximation value space. There's a paper that's online that you can find. Sequential decoding, sequential inference, and particularly the game of Wordle, the New York Times puzzle. We have a paper of application of rollout in this context with two of the students at ASU, Bambry and Bhattacharjee. And there's a work that I'm very excited about. There's joint work with Yu Chao, who is sitting here, and has to do with finding or approximating the most likely sequence in a transformer, a ChatGPT type of transformer. A transformer generates next words with some probabilities. And if you are at a certain point, you have a text window already that you have covered, then according to the transformer, there is a well-defined most likely sequence that will generate. You'd like to have that sequence in a number of contexts, although I can't point exactly where it would be most useful. But finding that sequence is an extremely difficult problem because the branching factor of the transformer is extremely large, right? And if it goes forward to any number of steps, it's impossible to find by enumeration or dynamic programming to find the most likely sequence. So we have used rollout in this, which is much, much more effective. Truncated rollout with some pruning, some intelligent pruning, and we have obtained very, very good results. And now this particular application also applies almost verbatim to a vast range of applications involving HMM, hidden Markov models. Okay, there's a very large number of applications. And again, the Viterbi algorithm, which is the central algorithm in this context, precisely finds the most likely sequence. And you can use instead the rollout algorithm to find an approximately optimal, approximately most likely sequence. And this applies to all sorts of HMM problems that involve a large state space and a large branching factor. So this is work that we have, we're looking forward to extend and to find good application contexts. We're looking for partners, in fact, in this area. So now I'm going to spend a couple of slides for Minimax problems. Okay, the nice figures that I gave you earlier with a concave Bellman operator and these tangents does not quite apply to Minimax problems. The reason is that the Bellman operator for Minimax problems is not concave. It's partly concave and partly convex. And Newton's method does not converge globally, or the region of convergence is kind of somewhat jagged for Newton's method. So there is this theoretical difficulty, and there's a motivation. This motivates using an approximation to the maximizing operator in policy space. In other words, approximate the maximizes policy by some fixed policy. And then the problem becomes a one-player problem for which the Bellman operator is more benign, and all the insights that I gave you earlier apply. So we replace the maximizer by a trained nominal opponent, some nominal opponent that looks reasonable. And this converts the two-player problem to a one-player problem, which we can address with MPC. So this is an idea that has broad generality in Minimax problems. And we are looking at various contexts, including linear quadratic games to start with, which admit some analysis, and other contexts. But I'm going to illustrate this with computer chess, which we've done considerable amount of work together with Atharva Gundawar, a student at ASU, Yu Chao and myself. And I'm going to give you some results. So we use this nominal opponent idea to convert the problem of playing computer chess using MPC. And we call this architecture MPC-MC, meta chess. Meta chess in the sense that this is a meta algorithm that involves as components other algorithms. So the true opponent is approximated by a nominal opponent. And for this, we use available chess engines, two engines. The nominal opponent engine, which predicts the move of the true opponent of MPC-MC, exactly or approximately. And then the position evaluator engine, which evaluates any given chess position. So at the current position, our architecture does the following. Consider all possible legal moves, and then uses the nominal opponent to predict the move of the opponent once. And then the resulting position is evaluated with the position evaluator engine. So one engine here to predict the opponent's move, a second engine to approximate the position. The result is backed up to the root, and the branch that gives you the best score gives you the move to play. Then the true opponent plays, and then when it's our turn to play, we use the same process. Now here, each move involves a Newton step, right? Because it's a one-player MPC. It also is more easily understood in terms of this region of convergence business and the visualization I gave earlier. And I'll give you computational results. Here is our architecture against a champion program, Stockfish. It's a very well-known program. It's used as a benchmark to measure the effectiveness of various other computer programs. So we use Stockfish as nominal opponent engine and position evaluation engine. And we play against Stockfish. Okay, so the actual opponent is Stockfish, and we also use Stockfish for nominal opponent and position evaluation. And we have a couple of different variants of the algorithm. Start in 45. 45 is a little bit more conservative. I don't want to go into the details, but here are some results. Okay, so our architecture using Stockfish as Stockfish as engines, playing against Stockfish. And each entry here gives you the result of a 10-game match. And we played against Stockfish of different strengths. At 0.5 seconds per move, Stockfish gives you a pretty good, is a pretty strong player, above master, approaching grandmaster perhaps. At 2 seconds, it's definitely above grandmaster level. It's a very strong engine. At 5 seconds, it's almost unbeatable. It plays almost perfect chess. So we use these engines for our architecture and also as opponents. And what does these results mean here? In computer chess, a win scores 1 point, a draw is half a point, and a loss is 0 points. And MPC-MC in all of these matches did not lose a single game. MPC-MC just does not lose against an opponent of the same strength as its engines. And so this means that MPC-MC scored 5 wins and 5 draws against this opponent. Here, 6 wins and 4 draws. As the Stockfish, the opponent, becomes stronger in strength, it's harder to beat. So for example, in this match, there was 10 draws and no wins of either opponent. However, the fortified version, we managed to score here 1 win and 9 draws. And there are 2 versions here, 2 types of results. One is when we know the MPC, we can predict the Stockfish response precisely, and when we can predict it only approximately. And for this strongest strongest opponent, the standard version on a 20-game match, it was 20 draws. And for the fortified version, we actually managed to get 1 win. So we had to go to matches of more than 10 games in order to score a win. Everything was coming out as draws because this engine plays almost perfect chess. It's very, very hard to beat. But we didn't lose a single game, and that's consistent with a lot of other experiments. And we have actually obtained better results when we used other engines. Like there's another engine called Komodo Dragon, which is not quite as good, at least the version that we had access to. It's not quite as good as Stockfish, but still very good. We got better results. We also got better results for transformer engines. This is an innovation in computer chess, whereby instead of looking ahead forward for many moves, you use a position evaluator that's very well trained, using a large language model of tremendous capacity, like 200 million, billion, I lose track of. Was developed at DeepMind to predict, to evaluate positions. So this engine works as follows. You look at all possible moves, and then you look at a position evaluator without going forward, like 20, 30 moves. So very, very fast. And it doesn't play quite as well as Stockfish, plays like a master level. However, when we wrap it up into an MPC-MC architecture, we get grandmaster performance results. And we just beat very decisively this DeepMind engine once we use the DeepMind engine as nominal opponent position evaluator. And that's significant because we can afford to do multi-step look ahead. The evaluations are so cheap that we can go forward quite a bit. So we hope that with this multi-step look ahead, we're going to obtain usable and fast performing programs and using this transformer engine. This is something that we work on. And now the other thing to notice is that even though there are a lot of nominal opponent prediction of moves, and there are a lot of position evaluation, all of this can be done in parallel. If you go back to this figure, there's a large number of the order of 30 predictions here, but they can all be done in parallel. And there are also a large number of position evaluation here, but they can all be done in parallel again. So the amount of computation that we need is about twice as much, assuming sufficient parallel computation power is twice as much the computation power that's needed by a single position evaluation. It's 1 step and 2 steps. So parallel computation is quite important here, and we have verified this with some parallel computation hardware, although not fully. There's more experimentation that's needed.
Dimitri, before you move from this slide, I have one question. So what if the position evaluator is less a less good chess player than the opponent? So what if you use Stockfish for the opponent and your position evaluator is?
Okay, the general things that we have seen supported by theory to a great extent is that if you use a particular engine as nominal opponent position evaluator and play against the same engine, then you obtain better results. In other words, give me any engine, I can improve it by using that engine, strapping it into the MPC-MC architecture. Mm-hmm. If I use a relatively poor nominal opponent engine, I can beat a relatively poor actual opponent. On the other hand, if I play against a stronger opponent, then that's not going to be true. So it's important to use a nominal opponent of at least equal strength and preferably even better to approximate the minimax opponent, generally speaking. So that's what we have seen. And based on insights from rollout, because there's some rollout involved here, it's there's a cost improvement property or performance improvement property. We have tried also another experiment. Instead of using a nominal opponent, we use a randomization, okay? We have some engine and we randomize over the predictions, okay? Instead of choosing the exact prediction of this opponent. And that did not work well. It's important to use a strong nominal opponent because by randomization, you may be fooled into making the wrong move because the randomization did not produce a very good move for the nominal opponent, and then things break down. So randomization does not work well in this context. You have to use the best possible maximizer, the best possible opponent that you can get your hands on. And you can do this very often by training, okay? You can set up adversarial scenarios and train using these scenarios and create an opponent. I'm talking about a more general context, like, for example, safe car driving, okay, context like that. All of this is very new, and we're trying to understand it. And also we try to understand why we get this amazing performance margins, performance improvements. And I think it has to do with pruning. Stockfish prunes a lot. Of course, the less it prunes, the better performance. The less it improves, the better performance it yields. But it prunes even at the very first step of lookahead. And MPC-MC does not prune at the first step of lookahead. And what we see from computational results is that MPC-MC and Stockfish pretty much generate the same moves most often. And then every 10 moves or so, there's a difference. And that difference may often correspond to a case where by pruning, Stockfish has moved the right move, the correct move, whereas we were able to figure out that move. And then from this move, we get an advantage, and then 2 moves later, perhaps Stockfish will slip again, and then a cascading accumulation of advantages can lead to a win on our part. But for the most part, our architecture and Stockfish, whatever the opponent is, they play pretty much the same moves. It's only a few times that they make a mistake due to pruning. It's most likely due to pruning, and they don't. No, pruning corresponds to deteriorating Newton step, and that's significant from a theoretical point of view. So there's a lot of work that we want to do here to apply to other contexts other than computers. And incidentally, all of this applies to any 2-player board game, any kind of game, like Othello, like a Chinese version of chess. It applies to Go, any kind of 2-person game that is that does not involve stochastic uncertainty. This framework does not apply if you have stochastic uncertainty. Only Minimax, only the Minimax context.
So, is there one more slide, Dimitri, or is this the last one?
Yeah, I have one more slide.
Oh,